Now let's look at an example of torque. So this is number 71 in chapter 10. And in this one I have two flywheels that are stuck together. We've got a flywheel right there and a flywheel like that. We'll call this radius R1, we'll call this radius R2. And we're pulling on the inner flywheel with a force 1 of 50 newtons, and we're pulling on the outer flywheel in the opposite direction with an unknown force. Okay, we'll call that F2. And we know that R1 is equal to 30 centimeters and R2 is equal to 50 centimeters. And the question is, what force do we need to apply to this system so that there's no rotation? So you can imagine if we've got a, maybe we're trying to design a brake for a pulley system and we want to be able to, deploy the brake in such a way that when we're hanging something off of it, it doesn't go anywhere. So the thing about torque is that it's going to act, we can employ Newton's laws the same way we would with forces. So if we have something that's not rotating, and where it's either, I should say, when it's either not rotating or rotating at a constant velocity, the sum of the torques have to be 0 because there's no net acceleration. So we're going to set the sum of the torques equal in this problem. Now, because these torques are both operating at 90 degrees to the radius here, I can write down the torque, say, being applied on the inner flywheel is just equal to the force times the distance. And the torque on the outer flywheel is also the force times the distance. And if I were to write the sum of the torques have to be equal to 0. And here's where I ask about the direction. And usually I use my right-hand rule to decide what sign the torques are going to have. So my F2 is going to tend to rotate this thing counterclockwise. So I'm going to call that a positive torque. And my F1 is going to tend to rotate it clockwise, so I'm going to call that a negative force. And since those are equal to 0, that just means they're equal to each other. And so I want to find F2, so I'm going to go ahead and solve for that. And I wind up getting F1 times R1 over R2, and that's just 50 newtons times 30 centimeters over 50 centimeters. Centimeters cancels, 50s cancel, and I wind up getting 30 newtons. So there's my solution, my significance. Well, let's take a look at this force here. This force applied, because it's acting at a further distance from the center, should be smaller than the force applied on the inner distance. And that's because we have a mechanical advantage because we're applying this torque, we're applying this force at a longer distance. So for the same torque, we get a smaller force. So this makes sense given that R2 is larger. There we go.